welcome everybody. It's a big pleasure to see a nice crowd here in the room, and I hope we have a few folks watching on the webcast as well. It's my big pleasure to welcome Volker Wulfmeyer today for our seminar. Volker is from the University of Hohenheim, Stuttgart in Germany, where he's a professor and director of the Institute of Physics and Meteorology. Volker is actually one of the bright, shining scientists in the Lidar world and has been interested in Lidar applications for the study of boundary layer meteorology for most of his career. Volker got his PhD at the University of Hamburg in 1995, followed by a short postdoc at the Max Planck Institute for Meteorology in Hamburg, before he moved here to Boulder, actually, where he spent some time at NOAA and NCAR, and just before I try to figure out exactly what time at NOAA and NCAR. And turns out back then, actually, the LiDAR groups were sort of working together. So I think there wasn't quite as strong as the distinction as there is today. He went back to Hohenheim then and became a professor in 2000, but maintained his contact here with NCAR. He's actually been affiliate scientist for a number of years, and I guess you've had other visits in the meantime. So it's my big pleasure to announce this talk on new LiDAR sensor synergy for studying and improving parameterizations of land-atmosphere interaction and entrainment in heterogeneous terrain. Please, let's welcome Volker.
Yeah, thank you very much, Holger, for the very kind introduction. It's a pleasure to be back in Boulder at NCAR, and thank you very much for the invitation. In my presentation today, I would like to give you an overview of efforts to combine LiDAR systems to study parameterizations of land-atmosphere exchange processes and entrainment, particularly in heterogeneous terrain. First of all, I would like to give you my perspective on key challenges in Earth system models. Then I would like to explain how active remote sensing systems can contribute to address these challenges. I highlight in this connection as the land-atmosphere feedback experiment, LAFE. It's an experiment we performed last year during August at the Southern Great Plains site in the US. So I will show some first examples from this campaign, how we would like to combine instruments to make contributions to process understanding. I end my talk with a summary and an outlook. Recently, at our institute, we performed, to my knowledge, the largest Earth system simulation with respect to the duration. This simulation covers a duration of 5 months and is nearly global from 60 degrees north to 60 degrees south. And we're using here the so-called convection permitting resolution, which corresponds to a grid increment of 2.5 kilometers. You can see here very nicely the line of tropical convection, which is recovered by the model simulation. This actually is from February to June 2015. The resolution of each image is 1 hour, so we can also observe the diurnal cycles. So this is now southern summertime, and you can see that the model starts to simulate nicely the diurnal cycle of convection. Furthermore, we see the extratropical transition which lead to formation of low pressure system. In the mid-latitudes, from time to time, the model simulates a cyclone or a typhoon. So this looks quite reasonable, and actually I think even some scientists will have a hard time to distinguish this model output from a satellite image. Nevertheless, when we now look at the details of the performance of this model, there are still some challenges. Yeah? The goal in the future is certainly to run these simulations in the weather forecast mode or to do climate projection. And the hope is that the systems will have a better skill to simulate the statistics of extreme weather, for example. And this also will require that we will have earlier or later ensembles of these nearly global simulations. However, when we looked in detail about model performance, and we still find some deficiencies. We find some deviations in the simulation of land atmosphere feedback, so an overestimation of cloud development, for example, an overestimation of tropical convection, some erroneous results in orographic terrain. But this indicates that we still have to work hard on the representation of the interaction of the land atmosphere system and to work on the parameterization chain from the land surface to the turbulent boundary layer to the formation of clouds and precipitation. And it's quite evident that we need to, in order to improve these simulations, very high resolution thermodynamic profiles. Now we have to resolve the surface layer, we have to resolve the turbulence in the boundary layer, and this is the major effort we are putting in, that we realize the measurements of three-dimensional thermodynamic fields, also with turbulence resolution. When we look around, however, currently, I must consider the measurement status in the boundary layer as terra incognita. They have basically no measurements of vertical profiles of thermodynamics. Okay, the highest vertical resolution we have is from radio soundings, but we all know that the temporal resolution is 12 hours, and this is definitely not sufficient to study the diurnal cycle of the boundary layer, land atmosphere exchange, turbulence, and so on. Another topic which is of interest of us is to develop metrics to study land-atmosphere interaction, and I would like to emphasize that particularly also the central plains in the US are regions of strong coupling between soil moisture and precipitation, which has been shown here in this paper. So our goal is to develop and apply remote sensing synergy for improving process understanding. First of all, I would like to show you some instruments we developed in this connection to make some progress. Basically, I'm talking about three instruments we developed at our university. The first system is a 3D temperature and water vapor Raman Lidar. 3D stands for the property of the system that we can perform 3D scans. The setup of this kind of Raman Lidar is in principle quite straightforward. We need a high power laser which is operating in the 355 nanometer region. This is separated by a prism to ensure eye safety. The laser pulse is sent into the atmosphere. The light is detected by the scanner and the receiver, and then we have developed a special polychromator which separates the signals with respect to the water vapor Raman channel and two temperature-sensitive channels. I would like to point out that the master of the system is now today sitting in the audience. This is Andreas Behrendt from our institute, and if you have further questions about the system development, I'm sure that he will be happy to answer all your questions. Here you can find also some overview of the system design and the performance. I would like to show you just a few examples of this system. This is a time height cross-section we measured during the field campaign at the ARM SGP site. And this is now a temperature profile shown in color scale. The resolution of each profile is 10 seconds. And the vertical resolution is 100 meters. And now we start to see the vertical structure of the atmosphere also with respect to temperature. Now you can see here the decrease of temperature, the increase again. So this is nothing else than the inversion layer we can now resolve with very high time vertical resolution. You can see that it degraded a little bit, but it maintained. So this is a daytime measurement actually. It's -6 local here, so it's
How real are all those high variations? Probably 10 seconds. Just look at the top red one.
Most of these structure is real. Yes, this is nothing else than the turbulence we observe. Now we see the updrafts in temperature and the downdrafts of colder temperature. We'll come back to this later when we analyze these turbulent structures. This is an average of the temperature profile over 5 minutes and 100 meters. Here you can see the error bars. And this helps us to distinguish in these kind of structure, fluctuations between noise and real atmospheric fluctuations. We can do this very well, and we can state in principle, on this time scale, we can make measurements with an accuracy of the order of a tenth of a Kelvin. This is now possible. So I think we can state that this is a really unique system with scanning capability, and the typical performance you can see here. When we average over 10 minutes and 300 meters, we can go up to 4 kilometers with an error of less than 1 Kelvin. And this is sufficient also to study the turbulent structure of the convective boundary layer. So this is system number 1. The second system is a water vapor differential absorption lidar, which has also 3D scanning capability. You may ask why we want to make measurements of water vapor with another system. The issue is that the water vapor dial has usually a better accuracy during daytime, better than a Raman lidar. And therefore, we put also quite a bit of effort in a system to get high-resolution 3D scans using the differential absorption lidar technique. I think I don't have to go too much in detail here concerning the dial technique, because also the experts are around. Scott Spooler, Tammy Beckworth developed a fantastic operational water vapor dial, which is, I also think, worldwide unique at NCAR. I'm sure that this has already been demonstrated and discussed. The main difference I can say is maybe in the technology we use in high power laser to push our measurements in direction of 3D scans. So we have a higher signal to noise ratio, which is mainly due to the high power of our laser transmitter. This is has an average power of 10 watts. And we use an 80 centimeter scanner. So the system is quite sensitive. So we can now go in direction of scans. I also would like to mention that the vision to develop the system here was actually started during my postdoc activity in '97, where Dave Carlson was still head of the ATD, and Timmy was around, and we came together to think about how can we measure 3D water vapor. And I think today I can say, yes, we realized this vision, and we now would like to apply this system to improve process understanding. Yeah, just in short, the design is that we use here the high power titanium sapphire laser, which is frequency stabilized to a water vapor absorption line. The signal is transmitted through a telescope, then the backscattered signal is received by the telescope and sent to an avalanche photodiode, where we then collect the signal. And this is our large scanning telescope here. Couple of further images. This is our mobile laboratory. It still looks quite dense with respect to the number of optical components on the table. This is the 80 centimeter scanner with the transmitting telescope. And here you can see Andrea Riede and Florian Speth during a field campaign in Germany. Let me show you some results of the performance of this system. This is a 3D measurement of water vapor we performed at the so-called HOPE campaign. It was a campaign back in 2013 in Germany. You can find further details. For one scan during this time, we needed 10 minutes, and we get a range resolution of 60 to 300 meters. So we start to see in this direction and in this direction the mesoscale variability of the water vapor field. In the meantime, we improved the average power of the system. We operated this here with average power of 2 watts. We have now 10 watts. This means we can make now one 2D scan up to a range of about 4 kilometers in 2 minutes. And then you can start to do a sequence of scans to recover the 3D water vapor fields within half an hour or so. And this is usually the requirement which is given to study convection initiation and mesoscale variability in the water vapor field leading to convection initiation. Yes, it's a now quite well-developed system. The error is of the order of 2% of the water vapor measurement. And when we measure with a resolution of 10 minutes, 300 meters up to 4 kilometers, we have an error of 1/10 of gram per kilogram, the mixing ratio. Again, this indicates right away that we can resolve turbulence with the system. I also would like to show you the system number 3. This is basically minimization of our water vapor and temperature Raman lidar. So we have here again the truck, where we have the 3D system, and then the new system looks like that. So just a box with all the electronics and the receiver inside. The nice thing is, of course, more compact. It's mobile. It can be transported. It can be operated continuously, but it has the same average power and the same efficiency. I would say even a better efficiency than our large system, because we improved the receiver in many ways. And here you can see an example what we can demonstrate with the system. This is a daytime simulation of the performance. We can go up to 5.5 kilometers with an averaging time of 10 minutes and a range resolution of 300 meters. And we have, under all climate conditions, temperature error of less than 1 Kelvin. And this is a simulation over different climate zones where we took the typical temperature profiles and the daylight background into account. This fulfills the so-called WMO breakthrough standard for nowcasting and very short-range weather forecasting. So we can say that this is a very promising system now to become operational, to deploy these systems in networks to collect more data. It has a higher accuracy and resolution of temperature and water vapor profiling during day and night time. It's eye safe. I would call it small, definitely smaller than the truck. Yeah. Operational and robust. The expected lifetime of the laser sitting here is about 3 years. So we don't have to work on maintenance of the laser anymore. This is, of course, very important. This was actually decisive for me to realize a system like that. Scanning this with this performance, of course, also possible when you combine it with a scanner on top of it. In the so-called Expo journal, there's a first publication about this system. And again, I would like to emphasize that it would be very interesting to compare the system now with the performance of the water vapor dial at NCAR, make joint campaigns, and get more experience really to realize in the future that these systems become operational for research, but also for assimilation of the data in weather forecast models.
Is this a combination of, again, a dial and a Raman lidar, these two things? Or?
No, this is just a Raman lidar.
Only Raman, okay.
Just Raman lidar. But as I explained, the advantage of the Raman lidar is that you can measure water vapor and temperature simultaneously. And when we put these data together, we get relative humidity, we get buoyancy, we get CAPE, we get SIN, so a couple of derived variables, which I think are quite useful for process studies. At this point, I would like to acknowledge our team who contributed to the system development. This is Andreas. This was a student who was around during the field campaign. This is Diego Lange, who's currently working on our compact system. Simon Metzendorf, our laser expert, who's mainly working with the water vapor dial. Florian Speth, who's also working with the dial and doing the data analysis. And Shravan Muppa, who's currently postdoc at our institute, also working on the data analysis. This is actually my wife, who participated in the campaign and supported us as strong as possible at the SGP side to make the campaign a success. Well, now how we can put these systems together to improve process understandings. We put quite a bit of thought into this, particularly during my research day at 2013 at a sabbatical here at NOAA and also at NCAR. And we came up with the following idea. This is now a sketch of the heterogeneous land surface and the heterogeneous soil. We can have crops and forests. We expect the corresponding undulations of the bound layer top and mesoscale circulations. Now we deploy this area with the standard instrumentation, like a soil moisture and temperature network, observation of the leaf area index and the albedo of the vegetation, and if possible also root water uptake of the vegetation. It's very essential that we know more about the state of the vegetation and its properties when we talk about land-atmosphere feedback. And then we have also the surface energy balance stations measuring the radiative, latent heat flux, the ground heat flux, and sensible heat flux. But how can we now connect these observations with 3D observations in the atmosphere? We came up with the following idea. Here we deploy a set of 3 LiDAR systems which have scanning capability. That's a water vapor and a temperature LiDAR system, as well as a Doppler LiDAR. So these now observe the vertical slices of the atmosphere. So you get the line of sight velocity, water vapor and temperature in 2D. However, we want also to get the wind field. And therefore, we need also other scanning Doppler LiDARs. So we can apply Doppler LiDARs in a vertical scanning mode, conical, for example, to get the horizontal wind profile. Usually we don't get these wind profiles to the ground, but we will need to do this to study the surface layer. So we installed another scanning Doppler LiDAR which is doing cross-track scans like this. And now at this crossing point, we get 2 line-of-sight components. Now the systems are scanning up and down. Consequently, we get the wind profile down to the surface, basically to the top of the canopy. At the same time, we measure also the water vapor profile and the temperature profile to the surface. And when we now look in the theory, how these profiles are connected to the fluxes, the Monin-Oberkopf similarity theory, then we get U star, the friction velocity, the sensible heat flux, and the latent heat flux. This assumes, of course, when we compare these profiles, that the Monin-Oberkopf similarity theory works. If it does not work, we can also detect it. It's also very important information. Then we have to think about how can we improve our understanding to fit all these profiles. And the final step is that we can now use different Doppler LiDARs, cross-track scanning, or maybe just one. So we get these crossing points, for instance, over an energy balance station. We can get it over different kind of land cover, in a forest or cropland. And this is currently our idea to make contribution to the studies of the surface layer, that we map out fluxes and the profiles of the key variables over a certain region. Simultaneously, we deployed vertical pointing LiDARs, and these LiDARs have nowadays the capability not only to measure the profiles now throughout the boundary layer, but also combine the measurements of turbulent fluctuations, like T prime, W prime, to get the sensible heat flux, the kinematic flux first of all, water vapor flux, all kinds of different variances. I will come back to this later. So that's presently our idea. And we realized this setup of instrumentation for the first time at the SGP site in Oklahoma.
How far apart are the LiDARs?
It's a very good question. This points to my next slide. Here you can see the realization of the deployment. Here at this site, we had the combination of the Doppler LiDAR, our temperature and water vapor LiDAR, and in a distance of about, horizontal distance of about 50 meters, we had the vertical steering system. So these were the Doppler LiDAR we used at the campaign was the so-called Dalek system of NOAA. It's a Leosphere Doppler LiDAR with very good performance. The scanning temperature and water vapor LiDAR came from our institute, so we brought it over the ocean and deployed it at the site. and the vertical steering Doppler lidar and the water vapor lidar to get the vertical structure was the Raman lidar from the ARM program operated at the site, and another Doppler lidar. We actually also deployed a third Doppler lidar from our institute to do scans to get also the horizontal wind profile. Then we added two other instruments, the so-called Spark instrument and the clamps, and they are operating Doppler lidars. And these systems realize the cross-track scans over different cropland, and in addition to that, we had three energy balance stations, 1, 2, 3, 4, actually four energy balance stations, and we were able to make the cross-track scans over these stations to make also comparisons of the derivation of the fluxes. And in the south, which is usually upstream of this site, we deployed the NCAR water vapor dial because we were also envisioning to do budget studies. So we need water vapor fields in 3D basically around the site. So the objectives of LAFE are to determine turbulence profiles and to investigate new relationships between gradients, variances, and fluxes. Map out, as I explained, momentum, sensible heat, and latent heat fluxes in heterogeneous terrain. Characterize land-atmosphere feedback and the moisture budget at the SGP site using the combination of our instrumentation. And finally, to verify large eddy simulation model runs over the site, which are actually ongoing already, and to improve the representation of turbulence in mesoscale models. Here you can see some photos of the instrumentation. That's a Spark instrument with a Doppler lidar here, operated by the University of Medicine, Wisconsin. The clamp system, which you can see we had quite severe weather conditions during some rain, some heavy rain, a clamp system by the University of Oklahoma, the NOAA Doppler lidar here. And actually we had also aircraft support to observe the heterogeneity of brightness temperatures around the site, which can be related to the vegetation state and the type of the crops. This is the SGP Raman lidar. There's a Raman lidar here, and here we operated two Doppler lidars. One was steering vertically, and the other system was operating in a scanning mode. This is an example of the NOAA ATDD energy balance closure stations, which actually measured the fluxes at two different heights, 2 meter and 10 meter. And also, actually, we tried to operate octocopters to fly around in a certain pattern to provide further measurements of temperature and water vapor fields. Here you can see our three amigos, as we called these during the campaign. The first time that we were able to deploy our dial systems with the Doppler lidar to get dynamics and thermodynamics at the same time. It's our dial system pointing along the line of sight we chose for the campaign, the temperature lidar, and the NOAA Doppler lidar. Okay, you can imagine, our systems are still challenging to operate the Raman lidar and the dial, and I was quite nervous when these systems were deployed on the ships, transported over the ocean, ending up in Galveston. Then we put everything on the truck, transported it to the site, and I was very happy that everything was there was nothing damaged, and the systems arrived at the site. And it took us a couple of days to get it running again. And during the campaign, they were running basically quasi-operational. We have a certain technique to turn it on, turn it off. There was absolutely no problem with the instruments. It's still hard to believe for me that this worked out this way, but this was really amazing. It was really extremely stable. Okay, now let me give you some examples how we can apply these systems to contribute to process understanding. The first example is to study surface layer profiles, gradients, and fluxes. I think I don't have to go to here, not too much in detail, what is typically done to relate gradient profiles to fluxes. We have the Monik-Obukhov similarity theory, which can be applied in horizontally homogeneous terrain, and of course entrainment. You expect that entrainment from the top of the boundary layer to the surface can be neglected. There are a couple of other requirements, but Monik-Obukhov similarity theory is part of each weather forecast and climate model. All these profiles are there, and basically there's usually just one gradient function for the unstable boundary layer, and that's it. Regardless where you are, over the ocean, over the land, you have this kind of similarity function. Okay, now we are able to measure these three profiles, but maybe also as well as the gradients, our instruments. So we can relate the wind profile and get U star. Then we measure the temperature and the water vapor profile, and we have our U star. Take the similarity functions and then get the fluxes. That's the idea. But this requires that we measure simultaneously water vapor, temperature, and wind with very high vertical resolution in the surface layer. And this has been done simultaneously. And it's not possible to do this just with one temperature profiler or so. And then we have the similarity functions which are proposed coming, for instance, from LES runs like Maronga et al. Now we can prescribe this in the unstable boundary layer. We plug this in, and then we have three measurements and three unknowns, and this equation system can be resolved. So as I pointed out, it is essential that we make these wind, temperature, moisture measurements simultaneously. Let me now show you an example, our first measurement, how this fits together from our campaign. Now, we operated the systems in alternating mode. We wanted to observe the boundary layer at the same time, but also the surface layer. So we made for 10 minutes scans from canopy top to 90 degrees to get a two-dimensional structure of the boundary layer, which gives us the boundary layer depth and 2D structure of humidity in this case. Each scan took about 1.5 minutes during this campaign. The range is 3 to 4 kilometers. You can see that we started in the late morning and continued throughout the evening transition. You can see the turbulent activity during daytime, and the 2D structure of the turbulent eddies. And what we observed, and I think it's more or less a general result, is that the entrainment always went down pretty close to the surface. So these structures you can see maybe in the surface layer may be related already to entrainment processes. Let me give you another examples where we did for the rest of the time 50 minutes surface layer scan. Each scan took about 7 seconds, go up and down, actually to go up. 7 seconds down, and then we have measure continuously the 2D field and the surface layer. As we do these kind of scans, the upper level changes from the near range to a couple of 10 meters to 400 meters in the far range. You can see the range of the water vapor measurement. Here the time is running, and this is now a measurement where we observed from the convective boundary layer over the afternoon decay to the evening transition. So here you still see some slight variability in the data, but later on you see that the surface layer is becoming stable, and then we see an accumulation of moisture in the stable surface layer with a thickness of about 10 to 20 meters. And now we can really observe these kind of vertical structures throughout from daytime to nighttime. And now it starts over again, and you can see also that all kinds of microscale or mesoscale features are moving through. We cannot talk at all about some kind of homogeneous structure in the water vapor field. Actually, I never saw a homogeneous structure in the water vapor field. There are always mesoscale eddies moving through, some microscale structures which may come from heterogeneity, differential evapotranspiration, which makes it actually hard to get profiles. Because in Monin-Obuchov theory, you think, okay, I average the data, say for half an hour, 1 hour, and everything is quite homogeneous, and then you get a nice profile. That's currently what we are working on. So all the time we see these structures, different scales. The scale is also from time to time changing because we have wind rotation and then advection of air masses from different directions. It's quite complicated. You will see gravity wave activity. And actually, when you look in the details, you see from time to time some waves moving upwards in the data, which are vertically propagating gravity waves developing at the top of the stable boundary layer. So it's now really fascinating that we're able to observe this. So what can we do about these data? Yeah, we challenge Monin-Obuchov theory in complex terrain. And already these observations indicate that new parameterizations may be necessary. Let me now show you an example of this measurement period. And we average the data over basically 1 hour. And we have here now our 3 profiles. The wind profile coming from the cross-track scans of the Doppler lidar. We can go down to the canopy top, basically. Well, increase of wind speed, this makes sense. That's good. Then we have the temperature profile, and we have the water vapor profile. Now, just to give you some features, when we average over this time period, which makes sense to make the comparison with flux measurements, we have an error of a few tenths of kelvins in the profile, and of the order of a tenth of grams per kilogram, or even less in the water vapor profile. This is a good performance, but it's also necessary to see the vertical structure, the water vapor field. Now we took, I also would like to emphasize that we should be able to close also the temperature profile here to the ground, but we have from time to time hard target returns when we scan up and down, and we need to clean up the data to get lower. But this should be also possible. For the dial, we did this already. Now, the vertical resolution is 2 meters for the Doppler lidar, 10 meters for the Raman lidar, and 3 meters for the dial. Now we took the observations from the tower. We made here the cross-track scan over tower 2, which gave quite reasonable results. A bone ratio of about 1, because we had some precipitation events before that. All the parameters we need for Monin-Obuchov theory. Then we took a similarity function, which is actually a routine profile produced in the Worf model in the convective boundary layer. Okay, I think I don't need to go through all the equations, and now we do the fit. And I must say, nothing is in agreement. The wind profile rolls off. The water vapor profile is totally off. And the temperature profile maybe a bit closer, but still, we were not able, with the surface observations, to fit our data to the Monin-Obuchov similarity theory. We played a little bit with the results. When you multiply this by a factor of 2.5, which is by far not in agreement with the observations, so we can come with a totally unrealistic combination of variables, and you can make the fit. But of course, this doesn't make any sense. So I'm looking forward to our discussion, how we can now move on. Of course, we have the idea that we study Monin-Obuchov theory more in detail. For instance, based on the research by Patton and al., so Ned is around today, because he already showed in LAS simulations that the standard Monin-Obuchov theory does not work, particularly if you have a large z naught value. So this is now our first result, and this is for us really striking how strong the deviations are between the standard similarity functions and our measurements.
How did you get your z naught?
This is just from our canopy measurement.
So
This was a measurement over soybeans.
can you use a curve fit to somehow use MO to reduce the z naught?
I think we should work on this, yes. So we need now a kind of range, optimize it, or maybe look for other similarity functions. Particularly, I think that interesting is that the weak vertical structure in the moisture. In temperature, I would say it's stronger, but in moisture, it's extremely weak. Please look at the scale. I forgot to mention this. I'll show you this profile. The humidity is between 11 and 11.5 grams per cubic meters. Now we are really able to resolve this vertical structure. There's a quite weak gradient, very weak gradient, and this is not expected by Munin-Urkow. Yeah, we are looking forward to work with you in the LAFE community to improve these and to understand these deviations. Okay, then let me come to another example, which is dealing with the convective boundary layer, particularly the so-called interfacial layer on top of the boundary layer. This is also a target of our research because we expect that also the turbulence parameterizations work not very well to predict entrainment fluxes. We developed in a couple of papers previously a first attempt to improve similarity relationships. We came up with 4 scaling variables for wind, for vertical wind, for exchange length scale in the interfacial layer, a scale of temperature, a scale of moisture. We relate this here to a length change and the gradient of temperature. Here the length scale and the gradient of moisture, which is a reasonable starting point. The length scale is related to the vertical velocity scale and the Wundt-Weisseler frequency at the top of the boundary layer. When we do this and want to study this, then we need to compare different kind of measurements. For instance, now we can derive from these scaling variables a relationship between the interfacial layer flux, the entrainment flux, and the gradient functions. And we also assume that there should be a relationship between the wind shear in the interfacial layer. This is this function where in the Richardson number is also wind shear included. So we have to measure 3 gradients, the moisture gradient, the temperature gradient, the wind gradient. And this is the reason that we measure water vapor, temperature, and wind at the same time at the site with very high vertical resolution. And then we need also the measurement of the flux. And then we can study these kind of similarity relationships. Then we get the flux measurement, we get the gradients, try to plug this together and hopefully get some agreements with this kind of relationship. You can do that also for variances. The variance can also be related to gradients. You can do some simplifications. For instance, there's an equation where the entrainment flux may be related to the variance and the temperature and water vapor gradient, or an equation where just the entrainment flux can be related to the variance. So there are very nice equations now we can study and we can improve. I think it's a very nice field of research using these LiDAR systems. And furthermore, I also would like to point out, I'm going to have to hurry up here, that we can also study turbulence parameterizations. Let me just explain this rather quick, going through the equations. When we take, for instance, the Worf version 3.9, that the standard parameterization is the so-called MYNN parameterization, which is based on the closure of the TKE budget. And this is a TKE equation, and when you look at this, we have TKE here, this E squared. And then we have a couple of terms like the momentum flux and wind gradient, and also the buoyancy flux. Okay, and also here we have the TKE dissipation rate, which is parameterized in this this approach, again by the TKE, in a certain order, and the so-called mixing length, the mixing length. Okay, when I now looked at this equation, I now wondered, okay, how are these fluxes parameterized? And this is basically the standard approach that the flux is related to the wind gradient using the turbulent exchange coefficient for momentum. Okay, now the question is, what is the turbulence exchange coefficient for momentum? And you find, okay, this is a length scale, the square root of the TKE, E, and the stability function. Now one not, okay, what is the length scale? And you find that is parameterized this way. It consists of a combination of the surface layer length scale, a turbulent length scale, and a buoyancy length scale. And the convective bound layer, mainly the turbulent length scale, plays the most important role. So I looked up, okay, what is the model doing to get this length scale? And you find, this is now becoming a function of TKE again, and this kind of integration over the vertical range of the boundary layer. And this can be measured. E, I will show you this, can be measured now. So we can already go deep in the comparison of turbulence parameterization. Okay, then I will not moved on here with these functions. What is now the stability function? Let me show you this for the heat flux, basically. Again, this is parameterized with respect to the the temperature gradient and the exchange coefficient, which looks quite similar to momentum. And here I looked a bit more in detail. So what is the stability function? And you come up with this equation. That's a function of these theta functions. And I looked, now what is theta? And finally you find theta, okay, is a function of GH. And what is GH? It is a function of TKE again, the length scale, and the temperature profile. And when I look at this term, it's a function of GM, and this is a function of wind shear, and also TKE. But all these values can be measured now with our lidars. We can measure the TKE profile, we can measure the wind profile, we measure the temperature profile, so we can actually put everything together, maybe to say that to give the turbulence modelers, I don't want to say a hard time, but let's say some productive data to make very detailed comparisons of their parameterizations. Again, this, with the sensor synergy, this is possible. Okay, is it really the case that we can make these kind of measurements? Indeed, we developed for one of the Doppler lidars a 6-direction steering mode. And with this steering mode, this is really, I must say, the unique data set. You can measure the wind speed as a profile and the wind direction, so you get the wind profile. Also here for 24/7, also on the stable boundary layer and in the turbulent boundary layer. We can get the 2-time height cross-section of TKE, and we can even get the momentum flux. And all these things can now be compared with the turbulence parameterizations. I would like to acknowledge that this is a development by the NOAA LiDAR team, Alan Brewer, Tim Bonin, and Aditya Chokulkar, who developed this scheme. And I think this is one of the best operation modes we have currently for a Doppler LiDAR. At the same time, we did also the vertical profiling. This is now an example during a vertical steering special observation period. So that's time height cross-section of water vapor with our dial. This is the time height cross-section of temperature. Now we zoom in between 213 approximately and 21 UTC. You get your typical temperature profile. We take the Doppler LiDAR data to get the W prime, the vertical wind fluctuations. You can see nicely the updrafts and the downdrafts. We take our water vapor, the temperature Raman LiDAR to get the temperature fluctuations. And you can really see that we are able to see these actually warm updrafts below clouds. This makes a lot of sense. And there, we need to resolve this. We can resolve this only when the system has an accuracy of the order of 1/10 of a Kelvin. And here you can see the entrainment. And now we can get the temperature variance profile, which is also quite useful for modeling. We get the third order movement of temperature, which has a peak in the interfacial layer. And then we combine the Doppler LiDAR data and the Raman LiDAR data to get the sensible heat flux. And this is our first output during this campaign, measuring the sensible heat flux profile. And I was quite happy to see that the sensible heat flux indeed goes negative in the interfacial layer with a value of the order of minus 50 watts per square meters, which is also typically shown in LES models. So the LAFE campaign, and hopefully also future campaigns, allow the simultaneous measurements of turbulence profiles, gradients, that we can put all this information together to study parameterizations or to develop new ones. In summary, I showed you today that a novel sensor synergy is available for the 3D studies of the surface layer, turbulence, and fluxes in the land atmosphere system. During LAFE, an excellent performance of all instruments was achieved, by far exceeding expectations. We performed 13 IOPs. 2 of these contain an evening transition, which is also nice to study, and one actually the solar eclipse, which took place on August 13 over the site last year. And we have already a paper on this, where we studied land atmosphere feedback during this really fascinating natural event. We can provide data of several special tests of vertical pointing and PPI scanning modes. We performed the first 2D measurements of water vapor and temperature fields from the surface to the lower troposphere, which are obviously challenging the Monin-Orkov similarity theory. So this is a great opportunity to work together on process studies and to collaborate between observationalists and modelers to make the models better and to improve parameterizations. The data of this campaign are already available in the ARM archive. Last but not least, I would like to mention that we are setting up a new observatory at our university, which we call the Land Atmosphere Feedback Observatory, where we will deploy this synergy of instruments. And this will give us a chance to make these kind of measurements routinely. Currently, during field campaigns, we have limited time periods of these measurements. At our university, I can just go out in my office, walk over the site with Andreas and our team and turn on the instruments all the time when we think there's an interesting event and get a much better statistical database. Thank you very much for your attention.
Thank you very much, Volker, for this very interesting talk. Any questions?
So when you have a Doppler LiDAR, wind, temperature, humidity, what's the typical sample volume? I know it's a laser, so a thin beam like a pencil, about 100 meters? Is that?
No, it's a few meters.
Few meters?
Yeah. The diameter of the Doppler LiDAR in the near range is 20 centimeters. In the far range, it's expanding a bit to a couple of meters.
Wow. Mm-hmm. And
this is what you're referring to, right?
Yeah, okay. That's what I'm. Because the beginning you said like 100 meter, 10
That's the range
seconds.
Resolution. That's the range resolution. When you look with the LiDAR in a certain direction, we need to average the data over a couple of range gates to get a good signal-to-noise ratio. It depends a bit on the system, how many range gates we have to average. For a Doppler LiDAR, just a single range gate is usually sufficient. And then you have, along the line of sight, 30 meters range resolution. That's a typical number. For the LiDARs, the range resolution is 30 meters for the dial in the near range. And this is degrading a bit in the far range and due to the decrease of the photon number in the signal. And for the Raman LiDAR, it's similar. It's maybe 60 meters in the near range, degrading to few hundred meters in the far range, depending where you are. But when you do the vertical scans, and I really would like to emphasize this, when you do the vertical scans and point in this direction, the vertical resolution in this scan is determined by the diameter of the laser beam. And this is a big advantage. And we have really an intrinsic vertical resolution of a meter or less when we do these kind of scans.
And related, so I noticed your water vapor cross-section, and they look very different signal as the range goes, a distance, So what is the range you really trust the measurement, within what distance? That's the next question.
This is actually very easy to determine because when we do these kind of scans, we can characterize each single beam with respect to its error. The problem is just when I now show you these kind of scans, it's very difficult to show simultaneously the error bars. Yeah. But we can determine this. When I, for instance, look here at a range of 1 kilometer and take one of these vertical scans, I can provide our data analysis basically also with a two-dimensional field of the error. And I can tell you that, I mean, in the near range, the errors are less than 1/10 of a gram per kilogram. And when you look at the scale, we have here about 12 grams per kilograms. And when you look at these fluctuations, then the error is basically negligible. But when you go to the far range and you see that the signals are getting noisier, then the noise error bars are becoming more important. And then we have to investigate how we can separate noise and the atmospheric structures. We do this typically with the famous separation of the atmospheric variance and the noise variance in the time series of the measurement, which was pioneered by Don Lenschow, who is also here today. And we do that routinely. When we look at the time series of the data, we can do that also in spatial sense. And then we get in this range an estimate of the atmospheric variance, an estimate of the noise. And if you average a while, this can still nicely be separated. As you could see in the Monin-Overkov profiles, I mean, the error bars become very, very small, even when you go out to 1-2 kilometers, when you average the data over 10-50 minutes. But this is an important point. Of course, we need to characterize this, but we can do this.
Any other question?
I congratulate you. You've done a nice job of finally putting this all together. I'm wondering, what's the likelihood that you can get beyond 4 kilometers horizontally?
The likelihood is actually quite good. These measurements I'm showing here are limited mainly in range because we did not send out all laser power. We had some eye safety constraints at the SGP side. We operated the laser with an average power of 2 watts. There was a maximum allowed power at this time to operate the LiDARs. But in principle, we're going to go out to 10 watts. With some measures like expanding the beam a bit more and some modification of the system, we should be able, when we get the permission to go operate with 10 watts, and then the range will double. I think we can get close to 10 kilometers with the system in one direction. Yeah. It's certainly a goal. I expected somewhat this question, how to extend the range, because it would be great, of course, to see more of the mesoscale structures around the system. It's, I think we can go out to 10 kilometers with an optimization. I also realized during the campaign actually that we had a little bit more background signal, solar background signal as I expected. And this will also help. We are currently working on to reduce this, and this will further increase the signal-to-noise ratio. So I think 10 kilometers should be feasible. And this is actually something we talked about 20 years ago when we started the system development. So we're getting very close there.
I really enjoyed the presentation. I was curious, what's this low end of the resolution of eddies you can resolve with the current technology? Have you done any spectral analysis of the data?
Yeah, we do that usually as a routine output that we look as a spectra, for instance, in the convective bound layer to analyze whether we are in the inertial subrange. Typically in the convective bound layer, we can resolve the inertial subrange. With a temporal resolution of 1 second, we go down far in the inertial subrange. That means that we resolve the major part of turbulence. And also when we play a little bit with range resolution, say between 30 meters or 60 meters, we usually don't see really a change in the spectrum. That indicates that we really, when we do measure the fluctuation, that these are really representative. But this is limited. You have to point out when you get closer to the surface, then I don't think that we can resolve the turbulence fluctuations anymore. They scale basically with the distance from the surface. And then the main limitation of our system will be the range resolution. When we go down to the surface and we have a range resolution of 30 to 60 meters, then we lose a major part of the turbulence, and we cannot resolve this anymore. And I think this is something it's very hard with a LiDAR to overcome, that we have the same resolution like an in situ sensor sitting at the height of 2 meters, where the distance between the sensors is maybe a couple of centimeters. I think this is not possible. And this is also the reason that we did not strive for the measurement of turbulence in the surface layer. We measure just the profiles. And this is allowed. This is what we can do. Now, when we have the range resolution, we measure the profiles, and the range resolution corresponds to a footprint of EC stations, and the profiles is representative.
Okay, one last question. Yeah, Don.
That's very impressive. I just wanted to ask you about the momentum flux measurement. Is that using this conical scan technique, or are you using instantaneous velocity measurements in the field?
This is not using the conical scans. It turns out when you do the conical scans, it's basically not optimal to get the turbulence profiles. It's much better to do the 6-beam steering mode, which you still steer in different directions and get the W prime U prime component in sufficient manner, but you are faster. The system steering in one direction over half a second, another half a second, and so on continuously, and then you can recover both TKE and momentum flux.
Okay, let's thank Volker one more time.
Thank you.